Okay, I'm gonna start to explain from the section 8 onwards because this is a relatively challenging topic, and I want to ensure that everybody is on the same page with regards to explanation and the understanding of this kind of questions. Okay, I think MCQ should be more or less okay. Okay, just go and revise for the MCQ portion. Okay, you need to understand the differences between the 5 structures that we have learned in this topic, and each 5 of the 5 structures, they do have their own kind of bonding. Okay, giant metallic is very simple and straightforward, right? It's mainly for your metals. For example, like copper, aluminium, okay, by themselves or even as in an alloy like steel, they will have metallic bonding. Okay, and they will have this giant metallic lattice structure. Okay, and they will have high boiling melting point, okay, strong electrostatic forces of attraction between the metal cations as well as the sea of delocalized electrons. Okay, conductivity is good in solid state because the electrons are free to move, and even in the liquid state. Okay, next is your giant ionic lattice structure, okay, which has ionic bonds. Okay, of course you have particles present, you have your positive and negative ions, and they are oppositely charged so that they will have strong electrostatic forces of attraction between them. Because of that, large amount of energy is required to overcome these strong electrostatic forces of attraction, leading to high boiling melting point. Okay, electrical conductivity when solid is very poor because these ions are unable to move as they are stuck in their fixed positions and are only able to vibrate. However, in the aqueous or liquid state, they are now free to move to conduct electricity. Okay, next, your small covalent molecules or your SMS. Okay, simple molecular structure. They are consist of small molecules which have weak intermolecular forces of attraction between the molecules, which means, for example, in water, between H2O and H2O, these forces are weak. Okay, which leads, because when you're melting or boiling them, you are overcoming these weak intermolecular forces of attraction. This leads to a low boiling melting point. Okay, however, there are also strong covalent bonds within the molecule. However, we are not breaking these strong covalent bonds when we are melting or boiling your SMS structures. Okay, therefore, it's not required to mention about these strong covalent bonds. Okay, just make sure you understand that within the one structure, you can have more than one type of bond with different strengths. Okay, next, in terms of electrical conductivity, it's very poor in all states because there are no free moving ions or electrons to conduct the electric current. Therefore, SMS always low electrical conductivity. Okay, next, okay, I'm going to do the GMS first. So your giant molecular, there is a large network of atoms. Okay, these forces between particles that are strong is referring to the intramolecular, which means between the atoms. Take note that only in graphite will you have weak intermolecular forces of attraction. In diamond and silicon dioxide, there are no intermolecular forces of attraction. Okay, because when you are boiling or melting your GMS, you are trying to overcome these strong intramolecular forces, these strong intramolecular covalent bonds between the atoms, whether is it between carbon atoms in diamond and graphite, or whether is it between silicon and oxygen atoms in silicon dioxide, the melting boiling point will be high. Okay. However, for graphite itself, graphite is an exception. Graphite has weak intermolecular forces of attraction between the graphite layers, and this actually allows the graphite layers to easily slide over one another, which leads to the property of graphite being soft and slippery. Okay, so in graphite's case, the weak intermolecular forces of attraction is not related to the boiling melting point, but rather the hardness of graphite. Okay, next, electrical conductivity in solid. Okay, For silicon dioxide and diamond, they are very poor in solid or liquid state because there are no free electrons or no free moving electrons to conduct electricity. There is no need to mention ions here because you already know that it is a covalent there is covalent bonding, so there will be no ions present. Okay, actually same thing for your SMS. There's no need to mention no ions present, just say no free moving electrons. Okay, so for your SMS and GMS, just say if they are unable to conduct, just say no free moving electrons. Okay, to conduct the electric current, therefore very poor for all except graphite. Why? Because graphite consists of each carbon atom being bonded to 3 other carbon atoms, which means that each carbon atom has 1 free electron. This electron is delocalized and is able to move freely to conduct electricity. That's why graphite is able to conduct electricity in all states. Take note, this free moving electron in graphite is not called the sea of delocalized electrons. The term sea of delocalized electrons only meant for metals. Only for metals. Okay? In graphite, all you have to say is the delocalized electrons itself. Can already. Okay? Next, I think the balancing, not much issue I already went through in class. Okay, remember the format for answering these very high melting point kind of questions using structure always entails first stating the structure. Okay, within the structure, explain the bonding. In this case, strong covalent bonds between silicon and carbon atoms, therefore leading to large amount of energy required, high melting point. Done. Okay, physical properties, not much issue. Okay, remember they are asking you to they are telling it has a structure like diamond. So please do not confuse it with your graphite. So remember, graphite is not hard. So graphite is actually and graphite actually conducts electricity. So I think some of you actually mixed up between diamond and graphite. So just make sure you understand that graphite is actually an exception of your GMS. Okay. Okay. Next, this question, okay, I just want to emphasize again. Remember, when you talk about your giant ionic lattice structure, okay, there are very strong ionic bonds or electrostatic forces of attraction. You can use them alternating. Okay, choose one that you like. Okay, they mean the same thing. Okay, but you need to mention that they are strong. Therefore, a lot of energy is required to overcome these strong electrostatic forces of attraction or strong ionic bonds. Okay, and remember when you explain this question for your comparing the melting point of magnesium oxide with potassium chloride. Okay, you have K plus Cl minus versus Mg2 plus and O2 minus. You cannot say that the charge of the magnesium oxide is double that of potassium chloride because the compound itself, the ionic compound, has no net charge. The charges are all balanced by the respective ions. Therefore, you must explain that the ions are the one that have the double the charge. The ions in the compound. Okay, so make sure you understand this. Okay, this one I think not much issue. Okay, remember for this font, for question 4a part 1, okay, remember when you say sea of delocalized electrons, only for metals will you mention the sea of delocalized. Graphite does not have a sea of we do not refer to the electrons in graphite as a sea of delocalized electrons. Okay, because there's significantly less electrons in graphite compared to your metals. Okay, you just need to say in graphite there is free moving electrons. That's it. Okay, property of titanium, just want to mention for your metals, pure metal, this one, they are not hard because of the regular arrangement which allows them to easily slide over one another when a force is applied. Okay, this question very important. This is very similar to the pop quiz question. Okay, where you have melting, where you have when they say this is forms a chloride. Okay, this chloride is formed with titanium. So it's actually a titanium chloride, not referring to a chlorine by itself. So read the question carefully. Okay, so because of the low boiling, low melting point, we can make a prediction that it has to be covalent bond. Why? Because SMS. Whenever you see low boiling, low melting point, has to be SMS because it is the exception of your boiling and melting points. Okay, so it does not suggest ionic or giant or GMS or even your metallic. So it has to be a SMS with covalent bonds. Okay, so what is the type of structure? It has to be SMS. And what is unusual about the answer? So you have to tell me what is different about this answer compared to what you usually expect out of that kind of compound. Okay, so based on titanium chloride itself, you know there is metal, non-metal, right? Most of the time, metals and non-metals will form ionic bonds. Therefore, this is unusual because this forms a covalent bond instead. Okay, next, question 5. Okay, question 5, they give you many substances with different the boiling point, melting point, electrical conductivity, as well as solubility in water. Okay, for your electrical conductivity, they did not tell you about the state. So it's not exactly very useful. Okay? So before you even begin, please develop the habit of trying to make a prediction of what kind of structures each substance will have. Okay, and the easiest one to make a prediction on is by your melting boiling point. Why? The moment I see low, low, it has to be SMS. Okay? What about E? High, low, high, not conclusive. Because it's probably an exception. Okay, so for your B, just double check. Electrical conductivity, SMS, very poor, correct. Solubility in water, insoluble, correct. So B is likely to be SMS. You can just put a tick. You know that it's SMS. Next, let's try to look at what A is. High boiling, high melting point. Good electrical conductivity and is insoluble in water. So A can actually be... Can it be GI? Your giant ionic cannot because it is insoluble in water. So most likely is giant metallic. Okay, because of the electrical conductivity. Okay, next C. Melting point high, boiling point high, poor electrical conductivity, insoluble. Cannot be SMS. Okay, cannot be giant ionic because poor electrical conductivity. Cannot be giant metallic. It has to be a GMS. Okay, for D, high, poor, soluble in water. Okay, so what D could be is probably a giant ionic lattice. I'll just put GI. Okay, why GI? Because remember your electrical conductivity, they did not tell you the state here. So it can still be a GI in solid state, because they are unable to conduct electricity in solid state. So for this case, for the GI, what is conclusive evidence is the fact that it's soluble in water. Lets you know that it is a GI structure. Okay, next, E. Low, high, good, insoluble. Okay, the fact that it's insoluble and good conductivity actually probably tells you giant metallic already. Back same as your A. However, why is the melting point low? Okay, it's because E is an exception to your regular metals. Okay. Lastly, F. High, very poor insoluble. Very poor soluble. Okay, most likely is a GI as well because it's actually the same as your D, except instead of very high, it is high for a melting point. Okay. Next, okay, let's look at part A. Okay, they tell you already substance A is copper. So you have already confirmed that it is a giant metallic lattice structure. So since A is giant metallic lattice, E has to be giant metallic lattice as well. Okay? So how do you explain why metals can conduct electricity? Because of the C of delocalized electrons. Okay? Next, part 2, apart from A, which is also a metal, is your E. Okay, why is it mercury? Because mercury has a very low melting point, therefore it is liquid at room temperature. It is an exception to most of the metals that you know. Next, give the letter or the substance that could be sodium chloride. Okay, that means it's a ionic or Gi structure. Okay, so it has to be D or F. Okay, next, give the letter of one substance that could be methane, CH4. Okay, you should know that methane is a SMS. Okay, because covalently bonded, because non-metal. Okay, if you have a non-metal being paired with a non-metal, it is confirmed covalent. Okay, the only exception can be between metal and non-metal, which can be ionic or covalent. Okay, in this case, your SMS is B. Okay, no argument because low boiling, low melting point. Next, dot and cross, I think not much issue. Just remember to read the question. Question asks for all electrons. So you must show the inner shell electrons for carbon. Okay, next section B. Predict two new properties of this new form of carbon. Take note that they said that it has small molecules, which implies SMS. Okay, so just take any two of the three physical properties for your SMS. Okay, molecular formula. Okay, you have not learned yet, but it's okay. You just need to take the relative molecular mass 720 divide by the relative atomic mass of carbon, which is 12. You get 60, means there are 60 carbon atoms in one fullerene. Okay, so the formula is C60. Okay, two other forms of carbon, diamond and graphite, they are also called allotropes, which means they are different forms of the same element. Okay, next, for your element mixture compound identification. Okay, I think not much issue. Just remember, if you know the formula, it's helpful to write out. Okay, of course, butane you might not know, so you could actually check Google. Ethanol is C2H5OH. Okay, potassium sulfate K2S. The carbon tetrachloride CCl4. Okay, ozone is O3. Okay, using this, you should be able to identify that butane, ethanol, potassium sulfate, and carbon tetrachloride are compounds. Ozone, take note, it has 3 atoms of oxygen. Since it only has one element present, it is an element. Same for bromine. Bromine is actually Br2. Okay, air is a mixture of elements and compounds. For example, element will be oxygen, compound will be carbon dioxide. Okay, brass is a mixture of zinc and copper. Sodium chloride solution. Remember, you see the word solution, what does it mean? Solute plus solvent. In this case, it is water as the solvent. So you will actually have salt plus water. So it is a mixture. Okay. Okay, carbon dioxide, dot and cross, not much issue. Just remember to pair up the unbonded electrons on oxygen. Okay, next, silicon dioxide. Okay, so remember this structure, okay, it resembles diamond a lot. Okay, diamond is one carbon connected to 4 other carbon. But for silicon dioxide, it's one silicon connected to 4 other oxygen. Okay, and each oxygen is connected to 2 silicon. Okay, so they tell you that carbon dioxide is a gas at room temperature. However, but silicon dioxide has high melting point solid. Use the diagram to explain this difference. Some of you misinterpreted the question as explaining why is it a gas, why is it a solid. Okay, there is no need to explain that, but rather focus on the boiling melting point at room temperature. That itself will allow you to differentiate the states already, because states at room temperature is dependent on melting and boiling point. Okay, remember this kind of question, when you say explain differences, you must tell me the differences. Okay, and you must involve structure. So first thing first, you must tell me that carbon, okay, let's start with silicon dioxide, GMS structure. Okay, bonded by strong covalent bonds. Okay, and a lot of energy is required to overcome them. Therefore, higher melting point. Next, your carbon dioxide has a simple molecular structure with weak intermolecular forces of attraction between molecules of carbon dioxide. Therefore, low amount of energy is required to overcome these weak intermolecular forces of attraction, leading to low melting point. This question is not asking you about the comparison of the bonds, whether it's single versus double. Okay, of course, double bonds do require more energy to overcome than single bonds. However, it really depends on what are the atoms involved. Okay, every different atoms has a different kind of a pull on the electrons, which requires different amount of force or energy to overcome. Okay, so you cannot make a conclusion based on the number of bonds itself. You have to look at concrete data, which we will add in the energy changes chapter. Okay, so for now, do not use the concept of this bonding, the strength of the bond to determine the boiling melting point. Just focus on the structure itself. Okay, the structure itself will be able to answer the question. Okay, and remember, when you talk about the weak intermolecular forces between molecules of carbon dioxide, there is no need to mention the strong covalent bonds between carbon and oxygen atoms inside each carbon dioxide molecule, because we are not breaking them. If we are not breaking them and we are not using them to explain why carbon dioxide has a lower boiling melting point, there's no need to mention. Okay, if you keep mentioning all this redundant information, you actually end up confusing yourself. Okay, so please be more selective with the type of information you are going to use to answer the question. Okay, just answer to what the question requires. Okay, next. Do you expect silicon dioxide to conduct electricity? Of course, no. Based on what you understand about your GMS, only graphite is able to conduct electricity. Okay, so the answer is just no free moving electrons. Do not mention ions, because this is not an ionic compound. There are no ions present. So it's like self-explanatory, okay? There's no need to explain why no ions are present, okay? No free moving electrons, as the electrons are held together in strong covalent bonds. Okay, take note that it doesn't, okay, this is a misconception that most of you have. When you compare graphite, okay, remember graphite is one carbon to three other carbons. Each carbon actually have one free unbonded electron that is free to move. Take note that in silicon dioxide itself, each oxygen atom also has 4 unbonded electrons. However, these electrons are not free to move. So this concept of whether or not they are free to move is not dependent on whether they are unbonded or not. Okay, actually it depends on some whole other concept as itself, okay? Whether or not they are able to separate themselves from the atom. Okay, so just be clear in your explanation. You just need to say that there are no free moving electrons. You don't have to explain about the fact that they are unbonded or bonded. Okay, if you are confused. Okay, if you can differentiate clearly, then you can tell me in this case they are all held together. Okay, instead of saying they are all used to form the covalent bond. Okay? Okay, next, why graphite can be used as a lubricant? Okay, this one just ignore. Okay, this one is weak intermolecular forces of attraction. Okay, van der Waals is actually the proper term that you will learn in JC. Okay, but for now, no need to mention this van der Waals force. Okay, so because graphite has weak intermolecular forces of attraction between the layers of carbon atoms, okay, each graphite layer, they can actually slide over easily when the force is applied. This leads to the fact that they can be used as a lubricant because soft and slippery. Okay, take note that for graphite itself, it does have intermolecular and intramolecular bonds similar to your SMS. However, the weak intermolecular forces of attraction in graphite is only overcome when you apply a force, which leads to the soft and slippery property of graphite. The strong intramolecular covalent bonds in graphite are the ones that you are breaking when you are boiling or melting graphite. So make sure you know the difference between graphite and SMS. Okay, next. Why diamond cannot be used as a lubricant? Okay, similar concept. You just explained the diamond have a strong rigid structure. Okay, you can tell me that the carbon atoms are bonded by strong covalent bonds in the structure, which prevent them from sliding. This is the key word. Okay, prevent them from sliding as opposed to graphite. Okay. Industrial use for diamond drilling or cutting tool. Some of you actually wrote what, sell for money. Okay, that's not industrial use. Okay. Okay, next, space station used to transport astronauts. Okay, whenever they give you this kind of information, please just read through. Okay, don't skip through them. Okay, they tell you that it's used to ferry transport astronauts to and fro from the ISS. When returning to Earth, temperature reaches over 2000 degrees Celsius. It's partly covered with graphite. Explain, suggest with reference to its structure why graphite can be used for this purpose. Some of you made the incorrect identification of what the question is trying to ask you. You thought that the question was trying to ask you that show that graphite has low thermal conductivity. First and foremost, we did not cover that in the syllabus, so you are not required to know that. Okay? I know that some of you actually googled to find the answer. Yes, graphite has low thermal conductivity, but that is not what the question is looking for. Okay? Remember, the question already stated here. Okay? The thing that we are trying to look at here is that why graphite has a high melting point. Okay? Or boiling point. Okay? So is this property of graphite is needed for the space shuttle to survive entry back into the Earth or take off. Okay? So in this case, you say high melting point due to strong covalent bonds within each graphite layer or within the carbon atoms in a GMS. A lot of energy is required to break, therefore high melting point. Always similar kind of answer. Okay? Last question. Okay, it's a very long question, 6 marks, but the format is exactly the same as even the smaller questions. Okay, they tell you boiling and melting points of three oxides, MgO, SiO2, and O are given. Explain in terms of bonding and structure why there are differences in the melting point. First and foremost, when they say differences, there is no need to compare specifically between two of them. Okay, this is more like a general comparison. Which means you tell me high or low. Don't need to tell me higher than this one, lower than this one. You have not learned enough to make that, to explain that. Why is this higher than this? Okay? So very straightforward. Remember, we always start with go one by one. See, 1, 2, 3. One paragraph on one substance. Okay? Firstly, magnesium oxide, giant ionic lattice structure because ionic bonding. Strong ionic bonds between oppositely charged ions. Large amount of energy required to overcome. High boiling melting point. Done. Don't need to compare this specifically to the others. You just say itself has high boiling melting point because relatively, I compare. This is high. This is high. 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 Low. Low. Okay, there's no need to compare between two. Okay, next, nitrogen monoxide. You know that it's covalent. SMS. Okay. Anyway, even if you don't know it's SMS, look at the boiling melting point. It's low. It has to be SMS. Okay. Weak intermolecular force of attraction between the molecules. Small amount of energy required. Low boiling melting point. Last but not least, silicon dioxide. You know there is a GMS. Okay. Strong covalent bonds between silicon and carbon atoms. Large amount of energy required to overcome. High boiling melting point. Done. Actually, it won't even take a lot of writing for this question because you just need to mention two things for each point, for each paragraph to get the 2 marks. Okay, structure and then refer to the energy required to overcome the attraction. Okay, that is all that's needed for each one. Okay, so that's how you get your 6 marks.